Yeah, so I'm going to talk about confidence and prediction intervals, and these are statistical terms, so I'm going to explain exactly what that means. But what I'm really going to focus on here are redundant microwave calibrations. So calibrations in which you've made more measurements than you need to fix all of the constants, all of the parameters in the calibration. And redundant microwave calibrations are really useful because the best calibrations are redundant because they're overdetermined. You're doing some averaging, but also because they have residuals. So what that means is that because you have more measurements than you need, you see some discrepancy between the measurements that you have and the models that you have and the calibration themselves. And those are very useful because you can use them to capture errors that you don't actually have a model for. And that's going to really be the focus here. An example, and the example that I'm going to use, are coupling corrections. We have a model for coupling corrections, but we know that that model is not perfect, that it leaves out certain things because the coupling is extremely complicated. The sources of the coupling change throughout the experiments, and that really makes it hard to do more than sort of a first order coupling correction, I would say. So we get those extra measurements. We get the measurements for doing the coupling correction by combinations of shorts, opens, and loads, and you can make that redundant by using a full set of different combinations, not just shorts and shorts and opens, but you can have shorts and opens and shorts and loads and so forth, and you can really build up a number of different redundant redundant measurements overdetermine the problem. Now, Ben talked about this yesterday, but correlations are really a key to maintaining the structure in the uncertainties that you develop, and this is going to be important later. But the point here, just very quickly, is that if your uncertainties look like a ripple in the frequency domain, they're going to look like a pulse in the time domain. And if all you have is error bars and you don't know whether that's a ripple, and instead it's noise, something else will happen. So it turns out that this structure is really important when you start talking about using residuals, because it actually fundamentally changes the approach that you have to use when you're trying to use those residuals to predict your errors. So I'm going to explain that in a little minute here. Okay, but first I'd like just to talk about microwave calibrations and regression. So both calibrations and regression algorithms are maps from sort of an input to an output. In the case of microwave calibrations, our X's or our inputs are typically measurements, and then the output, the Y's, are usually models during the calibration, and then when you put a DUT in, you look at its measurement, and then you try and use that to determine what the DUT actually looks like after you've performed the correction, applied the correction. So that's the DUT here is in orange. And they are usually overdetermined, although not always. And so often they're treated as regression problems where you have residuals that you try to minimize. And this equation here sort of illustrates that with the output. This is just a line, so AX plus B, and then each of these residuals here. And the goal is to use these residuals to try to help us determine the uncertainties when we don't really understand or have models for why all of those residuals don't fit with the calibration. So there is a community, statistics community that looks at these kinds of things, and when they talk about regression problems, they actually talk about confidence intervals in a slightly different way than we do. When we talk about confidence intervals, we usually mean a 95% confidence interval as opposed to the standard deviation of our measurements. But when they talk about confidence intervals, what they really mean is the error in the fit of the curve that they've in the curve that they've actually fit to all of these measurements. So if this is the line that we fit to these measurements here, the confidence intervals really reflect how accurately you know the parameters that define that line. That is, the A and the B terms there that define the constant value and the slope that define that line. Typically, these confidence intervals are dependent on where you are on the curve. So you'll have a higher degree of confidence in the middle of the curve to what the curve looks like, but then there's some uncertainty in the slope, and so you'll get confidence intervals that are sort of curved like this. Let's see. Okay. So what's wrong with this picture? Well, if you look at this picture, you notice that the measurement of the DUT sort of defines where the DUT is on the x-axis, and then our best estimate, our estimate of the output of this process, or the calibrated DUT value, sits right on this same line here. Now, does this really make sense? Well, all of these calibration measurements don't actually sit on this line. So we're actually missing something in what's going on. And this is where the prediction intervals come in. So in fact, the real value, the true value for this orange is typically not sitting on this line, right? Just like all of these measurements here. So the prediction intervals are an estimate of how far off of that calibrated line the orange sits. So now you see that there are these two aspects to the uncertainty. The first aspect is how well have you defined the line, the calibration line. And then the second aspect is how far is your measurement actually off of that calibration line. So this brings us now to the question of heteroscedasticity. So the typical approach, what you do is you look at all of these deviations of these measurements that define the line, and you use that as an estimate to give you an estimate of what the prediction intervals are for the measurements that you make around this line. And in doing that, you treat all of the apples as being interchangeable, as essentially being equivalent. And what heteroscedasticity means is that it comes from the Greek different dispersion, right? And what it means is that it's not necessarily true that the variance or the standard deviation of your measurements about this line are constant as a function of x. So, they could look like that. Right? You could really have a lot more variation for low x's than high x's, or vice versa. And this makes the calculation a lot more difficult, harder to do. You have to try to understand this heteroscedasticity to get your prediction intervals. So this brings me sort of back to the point that I made before, that correlations are a key to maintaining the structure that we need in microwave measurements to be able to do transformations between frequency and time, and between measurements that we have in time and then EVM and other metrics like that. So this is really important. And the issue here is that there's real structure on your DUTs and your calibration standards, and that structure depends on the DUT and the calibration standard itself. So this is sort of just a notional diagram, but you know that your calibration structures tend to be small, right? And in this particular case, for the coupling calibrations, they don't have any transmission coefficient, or at least a very low transmission coefficient. So all of your calibration structures live down here, and because they're small, they don't spin around too many times as a function of frequency, at least when compared to what you're measuring, which could be very large, may have transmission, so it not only goes through a different space, but then it has a very different kind of periodicity and spins around a whole lot of times. And even your calibration standards here are going to spin around at different rates. So that means that they're not really interchangeable. So this brings up a question of how you actually use your measurements in one sort of situation to be able to estimate what's going to happen in another situation. And the kind of solution is that you actually have to throw out some of the standard statistical things that people do when they're working with scalar quantities or just simple complex quantities. And because we have this structure, we actually have to go back to a sort of brute force approach in which you perform different measurements and calibrations, all of which are designed to give you the same answer. And then you look at not only the confidence intervals on these curves, but you also add that to the differences that you get from each of these calibrations and measurements that are all designed to get the same thing but don't. So it's sort of like repeatability and reproducibility, something like that, but it's not quite that. But it does mean that you have to use this brute force approach, not just to overdetermine your measurements to get the confidence intervals, but also make multiple measurements of the same thing to try to get your prediction intervals. So essentially what you end up with is a bunch of different calibrations. They're all designed to give you the same thing. They don't give you quite the same thing, but then you add your prediction intervals to your confidence intervals and you get a complete uncertainty. All right, so just to show you how this works in practice, this is an overview of the experiments that we did. We had one DUT, we had 3 different chuck materials, which changed the coupling, 4 different access line lengths, and we used this as a sort of example to try to show you how this works. And each experiment is designed to give you the same answer. So we moved all the reference planes to the same place, and they should give the same answer, but actually don't. So this is just a summary of some of those measurements. There were actually, I think, 7 or 8 calibrations involved, but and independent calibrations and measurements involved. But I'm just showing 2 of them here. They're in the red lines here. So the solid line here is the nominal value from one of those calibrations, and the solid line here is the nominal value from the other. And you can see the uncertainty around this result and the uncertainty around this result. And the first thing you notice is that they really deviate from each other. So the confidence intervals in this case are clearly not enough. They are not dominating what's going on. So you have to do something else to try to get your prediction intervals. And here you can see the average of all of these calibrations and the uncertainty in that average, and that sort of gives you your prediction intervals. And you can see that those prediction intervals are very large compared to these confidence intervals. Oops. So this graph shows the combined confidence and prediction intervals that we have. We have algorithms now that do this for a sensitivity analysis as well as a Monte Carlo analysis, and so there's just a comparison of the 2 of those. And now you're starting to see results where your total uncertainty is sort of indicative of what you imagine the spread might be in these measurements. And this is just for the magnitude, and then here is the phase comparison. Now, I mentioned earlier that in statistics, they do have approaches that for scalars and complex quantities where things are interchangeable, and I just wanted to show you how that actually compares. So this is what happens if you apply the standard approach that you might see in a statistics textbook and try to get this to work as compared to what we were doing here. And you can see that you really do get this compression. You really don't get the prediction intervals correctly by looking at the confidence intervals. It's very, very easy to do this. So this sort of motivates now the use of this brute force approach rather than just looking at the residuals in one problem and trying to estimate the uncertainty in other situations. Okay, so to conclude, for modeling problems, confidence intervals are actually sufficient, and that's what we're looking for. We want to know what's the uncertainty in our line. If you're trying to develop a model for a transistor, for example, confidence intervals would be perfect. But for calibration problems, where you're actually trying to then map a DUT through the calibration and find the corrected value of the DUT, you need both confidence intervals and prediction intervals, and you have to add them together. And you never know ahead of time which is really going to dominate. In this particular situation, it was the prediction intervals that dominated, but it doesn't have to be that way. You know, they could be comparable. You just don't know until you do the experiment. And I didn't have a lot of time to talk about the scalar approach, but the scalar approach does fail, and I just wanted to let you know that. In case you see this in a textbook, you'll understand that our situation, what we have to deal with in the microwave community, this structure in the errors really changes the way that we have to approach that. And I wish that I had more time. We do have some very interesting algorithms that we've developed. Ben gave you a little hint of that yesterday, what these algorithms look like, and won't be able to talk about them here, but in any case, I really appreciate your attention, and I hope that we'll be able to publish on those soon. Right, thank you very much.
Thank you, Dylan. We got time for one or two questions. Quick questions, please.
Okay, well, I'm glad that you all now understand confidence intervals and prediction intervals.